CTC 114. You've survived! You survived the first round of laboratories that we've given you. If you look at those labs, what do they have in common? What they have in common is that they all forced you to work with compounds and report something that we call physical properties. Okay, so basically what that means is that you have done things like density, you've done things like melting point, you've done boiling points, you've done refractive index on these compounds that we have provided you to a lab. All of these, if you were working in a wet laboratory environment, would be used to help ID your compound. And that's pretty important. You know, that is a lot of what we do in a laboratory environment. So I've got to be comfortable with working with physical property tests and performing these tests on these things that are given to me, and then reporting those values that I find in a laboratory environment. So density, melting point, boiling point, refractive index, on and on and on and on it went. Well, we also did a little bit of getting acquainted with things like balances, which are pretty important. And we've done things like working with volumetric pipettes and micropipetters. And the reason is because sometimes those are used to basically go through and report one of these other, or one of these that you see on your screen, physical property reports. All right, now what we need to do, we need to turn the corner. And we need to get comfortable with the concept of pH. Okay? Everything you ever want to know about pH is coming your way. Yeah, maybe more than what you want, but it is something that we have to become commonplace with. You know, going into a laboratory, doing my job every single day, there's probably a chance that I'm going to have to at least use pH directly or indirectly in some form or fashion. I might not understand that it's in there, but it will be in there. So one of the labs that you've done up to this point maybe included nickel DMG, and nickel DMG had a buffer component in it. The buffer component was required because it ensures that that reaction stays above a certain pH level. All of that was pH related. If I didn't control that and allowed the solution to go into the acidic side of the house, then my nickel DMG precipitate could have dissolved and went away. So this particular lab is an intro. It is an intro to pH. It's an intro to how we measure pHs, and we play around with a little bit of household solutions. Yeah, I know it doesn't sound very exciting, folks, but that's just the way that it is. I mean, this is the way that we get you into the lab and kind of get you familiar with what's getting ready to go on. So pH of household solution. I about lost my voice there because I was so excited talking to you about pH. Okay, so let's go through and give you at least some definitions. You want to? Let's talk about definitions. Part of chemistry, part of a laboratory environment, working in a laboratory environment is vocabulary. Okay, we want to sound smart, so we've got to be able to use the words that make us sound smart. And two of those words are acid and base. Now, there's tons of different definitions of acid and base that are out there. I can go through and give you at least 3 to 4 different sets of definitions that correspond to acid and base. The one that we would like for you to know right now, the term acid is basically something that we call a proton donor. All right, proton donor. And then the term for base we would like for you to know at this point is a proton acceptor. Now, I'm not going to go into the theory of which definition that I've just provided you. That's for a general chemistry class. That's not for here. So a proton donor and a proton acceptor. Well, what on earth is a proton, you might be asking, especially if you've not had a general chemistry course before. Well, a proton is just another word that represents H+. This is a hydrogen, and that hydrogen carries a charge. Now, I am going to go into a little bit of chemistry here, so just bear with me for a second. On the periodic chart, you're going to find hydrogen at the very top to the left. It's the very first one that's listed in the periodic table of the elements. It's the simplest. Well, this hydrogen up at the top has a 1, and the hydrogen down below has another number, and I'm going to round it off, and it's like 1.01. What do those mean? Okay, well, the number 1 up at the top is what we call the atomic number. And the atomic number represents something pretty important. It represents the number of protons. Oh, I see, the proton number. I just called this thing a proton. An acid is a proton donor, and now this atomic number represents protons, so I can maybe see where this is going. But it also represents the number of electrons. So in the field of hydrogen, hydrogen has 1 proton, and it also has 1 electron. A neutral hydrogen atom, straight from the chart, has 1 proton and 1 electron. Well, there's a third particle in here that we can talk about, and that third particle is called a neutron. Okay, well, how do we get neutron? It comes from the periodic chart. It's not a number that you have to memorize. It's nothing from a table that you have to go through and memorize numbers from. In order to get the neutron number, well, you take the mass number, 1.01, and you subtract the atomic number from it. And what we end up with here is a 0.01, which is pretty much there's nothing there. Okay? Well, why do these numbers have like weird decimal places? Okay, well, the reason they have weird decimal places is you have to keep in mind that the mass number down here is an average. Atoms are very much like people. We have super skinny beanpole atoms, and then we have quite large, pretty fat atoms. That's just the way life is. People are the same way. I'm not making fun of one or the other, but atoms are very much like people. That mass number is an average. It's an average of all of the hydrogens that might be out there, including the big ones and including the tiny ones. Well, at the same time, there's other things rather than just protons, electrons, and neutrons. These are what we call our 3 subatomic particles. Subatomic basically means below the atom level. So when we talk about the atom, what we're talking about are 3 subatomic particles: the proton, the neutron, and the electron, mostly. And the protons are going to be in the center. The neutrons are going to be in the center. And the electrons, whee, around and around they go. They're like little kids, again, high on chocolate, out in the football field running around like crazy. Mama and Daddy just sends them out, let them run, let them go wild, barricade them into a field, and then they just say, come home a little bit later, woo, and they go take a break and probably drink a glass of wine. Those are electrons. So in the field of acid and base, what we're talking about here is a proton, which is a hydrogen that carries with it a positive charge. In order to get this positive charge, that means that a negative charge has to go away, because right now this is neutral. The charges are equal. I know they're equal because look at this. Proton number equals electron number. So because they're equal, this thing is neutral, there's no charge, but lo and behold, if we send one of our kids out into the football field and tell them to go bye, and then this electron, whee, goes away, we end up with a proton only at this point, and that proton carries with it a positive charge. Well, we've lost the negative, it was neutral, and if we lose a negative, we now have more positives that are lingering around. And this is where that H plus symbol comes from. That is called a proton. And the reason, folks, only really a proton is left. That is why we call H plus a proton. Look, it doesn't have any neutrons. Nothing. We said 0. If it loses an electron, it goes away. What's left? The only thing that's left is a proton. So that is why we say an acid is a proton donor and a base is a proton acceptor. The proton name is coming from just simply a proton as far as subatomic particle goes, but we write it as H plus because it really is hydrogen that has lost an electron at this point. Now, that's the definition, one set of definitions for an acid and base. There are others. And something else that I need you to be aware of is this definition of what we would call strong and what we would call weak. So we have strong acids and strong bases. And we have weak acids and weak bases. And you are one of the other. And the reason that I say that is because strong acids, let's talk about them first. Strong acids will donate all of the proton that it can to the solution that it's in. Okay? In other words, you have a paycheck. You get your paycheck that day. If you are a strong acid, you would spend every single dollar of that paycheck all at once. All in one fell swoop. Cha-ching! There it goes. And you will not see another paycheck for maybe 2 weeks or a month. Are you that type of person? Are you that type of person that will get the dollars, stuff them in your pocket, and then by the weekend's over, all the dollars are gone? If so, you're acting like a strong acid. The strong bases, those are the stores that you visit. Those are the bars that you patron. You go up, you give them the dollar. The stores and the bars and everybody else takes the dollars from you. Okay, yeah, give me more, give me more, give me more. That is a base. That is a strong base. These strong bases will accept all of the protons that it can from the solution. Now, could you imagine going into a store wanting to spend money and the store says, "Oh, I'm sorry, we took enough money today. Could you come back tomorrow?" Okay, that's probably not going to happen, especially in Wilmington. It's not going to happen at any of your downtown restaurants or bars that you might visit. But that's the definition of a strong ace or acid and a strong base. Now, on the flip side of that, we have people that are a little bit more conservative. Okay? What they do is that they get their paycheck and they're like, we need to pay some bills. We need to kind of write out the checks, water, rent, cable, all of that's taken care of. I have a little bit of cushion as far as some extra money that's left over. We don't need to go to the movies this weekend. We don't need to go out and eat this weekend and spend $200 on a fancy dinner that you're just going to probably poop out tomorrow. Down the toilet goes to $200. Stay away from Ruth Chris Steakhouse. Well, those are weak acids. So what happens here is that if I have a weak acid, they do donate protons. They do, because that's the definition of an acid. But they do not donate all of them. That's pretty important. They keep some back for a rainy day. They have a little savings account that they put some of their protons back up into, and they're like, we'll spend these when the time is right. If we get put into a pinch, maybe one of us might lose a job, right? Maybe we need to move. Maybe something will come up and we get a bill that we didn't plan for. We have a nice little savings account of hydrogen that we can use to pay for those things. That is a weak acid. Are you a weak acid or are you a strong acid? Well, but probably depending on your age. I don't want to be ageist, but that's basically the way it is. Right out of high school, right out of college, or during college, you probably have no concept of bills at all. Spend, spend, spend. Do whatever you want to do. Spend it on crazy stuff. But when you get married, you've got a family, you've got other responsibilities, you are more prone to become more of a weak acid type of person. You save some of it back just in case something happens. You've got a backup plan. Well, weak bases are kind of the same thing. They do accept the protons. That is great for them, but they don't really take everything up. They do take them up because that's their definition, but not every single thing. That's the way that I want you to kind of envision the field of acid and base as of right now. In a general chemistry class, you might be presented with something a little bit different. You might be given extra definitions for an acid and base. You might be explained strong and weak acids or bases in a slightly different way. But for us right now, this is all that we need to know in order to go through this very first lab experiment together concerning pH. All right. Now, let's kind of expand this idea a little bit more. And when I say kind of, I mean really with a math equation. Oh no, math! Nobody said math was going to happen. Nobody said I needed a calculator. Well, you do. In pH, you probably will always need a calculator on hand. So just be prepared. That calculator on your phone will be good enough. You've got a scientific mode probably on that calculator. Or if you want to go fancy and get a scientific calculator from Texas Instruments and spend $150, $160 on it, bring it on into the lab. You're more than welcome to use those. That's what I have. I've been using it for years. Change the batteries and away it goes. So what you're seeing on the screen right now is a pH scale. So we have talked about definition of acid. We've talked about the definition of base. And what we have really just recognized from the very front image, the very front slide that's coming along with this lecture, is it really all has to do with hydrogen, right? Is it giving away all the hydrogen? Is it giving away some of the hydrogen? It looks like hydrogen is scattered through here quite a bit. So in order to really measure hydrogen concentration, that's really what we're after here in pH land. Okay, so hydrogen, which is really proton, H+, we really want to focus on the concentration of how much is in solution. And that concentration is typically going to be measured in something that we call molarity. And molarity is abbreviated with a capital M. So if we can measure the molarity of my proton or the hydrogen ion concentration, because this is an ion, right? We know what an ion is, a cation, because it carries a positive charge. If we can measure the hydrogen ion concentration of a solution, then we can do something that we call pH. We can put it into an equation. Because chances are this molarity might be like 0.00000 blah, 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 blah. Who wants to write down that silly little tiny number? I don't. I don't want to take the time to write down those extremely tiny numbers when I report pH or when I talk about pH. So what people decided to do is they're like, okay, fine, we know you're a little bit lazy. We know that you don't want to write down all of these digits. We know that this super tiny little number is somewhat inconvenient. So what we'll do is we'll allow you to take the concentration of the hydrogen that you are measuring. In terms of molarity though, right? You got to keep that. And if you log that number on your calculator, you just push the button log. That's all you got to do. And you negative that value what you will end up with is something that we call pH. Now, here's the thing with pH. P, a lot of the times in these chemical calculations, represents negative log. That is what P represents. Not to go PP, it means P negative log. So we negative log the H concentration. Folks, that's all that we've got to do. Okay, so for instance, if you're taking a general chemistry class, you might be at a point where you could be talking about pKa. What is pKa? Okay, well, you already now know P means negative log. And whatever Ka is, I'm going to negative log the Ka value to get pKa. That's how this is set up. The equation tells you all the details. So if I need to calculate the pH, I literally just take negative log of the hydrogen concentration. So for instance, if I get a word problem, and the word problem says, oh, you've got hydrochloric acid, and the hydrogen ion concentration of hydrochloric acid is 0.0034 molarity. What is the pH of this solution? It makes it sound more complicated than what it is. So you start with the pH equation, negative log of H plus, and you look at this number and you go, oh, there's my concentration. My concentration of H plus goes into H plus in the equation. So to calculate pH, I do negative log of 0.0034. You just basically cram this right into your calculator. That's all that you've got to do. And you enter it in the same way that you have wrote it on a sheet of paper. All right, so there's the log button if you've got a TI 83, 84, or any of the above. Right there it is. So I'm going to key in negative, which is down here at the very bottom. That's where I'll see that. There's my negative. Log of 0.003 and 4. And then I hit enter. If you don't have one of these fancy calculators, it's fine. You probably have a log button. The order of which you enter it in might be a different way, but your log button is going to be present. It's just a matter of how do you actually use it. Do you push it before the number or do you push it after the number? That depends on the calculator manufacturer. All right? So there is your log function on a calculator when you need it, and that is how we solve these types of problems. Now, the issue here is that sometimes they make us go backward. All right, so what that means is that sometimes they'll say, hey, you put a hydrochloric acid solution in the lab, and you measured the pH of that solution, and the pH of that solution is a 2.57. What is the hydrogen concentration of that solution in molarity? Again, they make it sound more complicated than what it needs to be. You literally start with the same equation, pH equals negative log of H plus. So the problem gives me pH of 2.57. Well, here's pH. Right there it is. I see it written in the equation. So 2.57 goes there. Equals negative log of H plus. Now I have to solve for H plus. This could be a little tricky, especially if you're rusty on your math. But watch me. Watch me. I'll show you how easy this is too. Get rid of the negative. Move it over. We've got to isolate the H plus on its own. So how do we do that? Get rid of the negative. Negative 2.57 equals log of H plus. Now we've got to get rid of the log. If we can get rid of the log, we can get rid of the H. We can get the H plus on its own. That's the purpose of any algebra equation. Bottom line, right there it is. So how do we get rid of the log? We do the opposite of. If that was H plus minus log, you would do the opposite of minus, which is add. If it was plus log, you would subtract. If it was times log, you would divide, right? If it was divide by log, you would multiply. That is how you solve all the algebra equations. You do the opposite function. Well, this is log. It's not just a simple function, but it's on your calculator. If you ever forget what the opposite of log is, go to your calculator, find the log button. It's right there. Do you see it? And the way that these scientific calculators are made, up above it, in the blue, you typically have to hit that second function button in order to get to that. It will tell you what the opposite of is. The opposite of log is 10 to the exponent. That is why those are there, folks. Bet you never really understood that, did you? Didn't even pay attention to that. But they always pair the inverse function with the main function on your TI calculators. So what that means is that if I have to get rid of this log, I'm going to do 10 to the whatever this value is over here to the side. So 10 to the negative 2.57. And that will give me the concentration of the hydrogen ion. It's as simple as that. So two equations, if you're uncomfortable with this, pH is equal to negative log of your H plus. So you would use that equation if you had your hydrogen concentration and you wanted to solve for your pH value, right? If you do not like the algebra that's wrapped up into this kind of quick solving for the H plus, then you have to memorize another equation. And that is hydrogen concentration is equal 10 to the negative pH value. That is what this boils down to. All right, so there's two equations. We're going to have to start getting a little bit more comfortable with these, and that is your first time in this class that you have ran across those two equations. Something else I need to talk about pH before we start the lab. pH is a scale. Whoop, there it goes. In the middle, 7. 7.0000000000000. That is neutral. This is what we regard as neutral, and the reason that we regard it neutral is because this is where our hydrogen basically equals our OH concentration. That's a conversation to have on a different day. But because those two are equal, we have a pH of a 7. So anything below a 7, typically the pH scale is written to a 1 to 7. This is the acidic part of the pH scale. And then anything above 7, typically it's written to 14, is going to be the base part of the scale. A couple of things to mention here with the pH scale, not to confuse you, but it is something that people look at and they do get bamboozled over or bamboozled over. The acidic side of the house means that you have a larger hydrogen concentration, even though that it's a smaller number. And the reason is because of this crazy little log function that's present. So as your hydrogen concentration goes up, you have more and more proton. If you have more and more proton, you are more acidic. And the acid values go 1 to 7, the lower end of the scale, and that's due to the log function that's present in that equation. As your concentration of hydrogen goes down, you start to venture over onto the base side of the house. So we have less and less and less proton, and as we have less proton, the solution becomes more basic. And this goes between 7 to 14. This is the higher side of the pH scale. But it's the higher side, again, because of that crazy log function. It makes things go backward on us. So here's the pH scale. But here's the thing that they don't really tell you in a science class. At least not the ones that I know of most often. pH can actually go lower than 1. We can actually go into the negatives. We can have pHs of -2s and -1s and -5s. I mean, this is not uncommon. It's not surprising. 1 to 14 is what we would call the working range. This is what you would see most of the time in a lab. But we can go pH of 0. We can go pH of -1. That's perfectly fine. No one said that we can't. They just don't talk about it. And that also means that we can go above a 14, so we can go to like a pH of 20. That's perfectly okay. It's just something that people don't discuss and talk about, but we can do it. No one says that you can't. So pH does go lower than 1, and pH does go higher than 14. It just so happens, though, that the working range that we see most often in a laboratory environment goes from 1 to 14, and that's the reason that they focus on that part of the scale the most. So here's a pH scale, and the purpose of this lab is to basically take household solutions like you're seeing right here, maybe some of them, and just measuring the pH of them, see what we get. That's all that this really lab is going to do. It gets you acquainted. It's your first date with the pH. So don't let us catch you in the corner making out with the pH probe. This is just the first date. You can do that a little bit later on your second or third date, but not on your first. So on the pH scale that you see on the screen, we have acids to the left and we have bases to the right. The acids, these are your 1, 2, 3, 4, 5, 6, and up to 6.9-ish pH. And what we see on this scale are things like gastric acid. Ooh, that's hydrochloric acid, folks. It's just hydrochloric acid that's weakened down and put into your tummy. So as you walk around the lab every day, what you're doing is you're carrying around a little sack of hydrochloric acid in your body, and that's in your stomach. But we also have things like lemon juice and apple juice and tomato juice and black coffee. There they are. All of those are acidic. Even milk is slightly on the acidic side. All of these also could contribute to an upset tummy. When you start to get indigestion, when you start to get a heartburn, when you throw up, all of that really sour kind of taste, all of that burning sensation that you get if you do throw up, all of that's due to the gastric acid that's in your stomach. It's all acid-based. Well, pure water, just H2O and that's it, should be a pH of 7. And then we start to get on the basic side of the house. And these are things like eggs and baking soda. Hand soap is basic at your house. Cleaners like ammonia and bleach, those are basic. So they do their job a particular way, and that's because they are basic. And you're going to have some household chemicals or household items that are basic as well that you're going to be testing in the lab today with this particular experiment. The concentrated solutions of alkalis that you see on the right-hand side of the screen here, the alkali is a term that just simply means base. That's all that really means. Fancy term, again, it's all words, it's building vocabulary, and concentrated solutions of alkalis is just concentrated solution of a base. That's all that means. So the question here is, if this is the pH scale, then how can we test the pH of these solutions, right? And there's going to be a couple of ways, and you're going to be doing those in this lab experiment. So the first way that we are going to be measuring pH is through something called litmus paper. Now, you probably have just encountered a lab experiment using litmus paper to ensure that you are on the acid side of the house or the base side of the house. And litmus paper, normally we talk about two different versions. There's actually a third, but the two versions that we talk about are red and blue. Okay, so red litmus, what does that mean? Well, that means it's a strip of paper, and that paper is going to be reddish in color. And blue litmus. Okay, well, what's blue litmus? Well, blue litmus is a strip of paper, and as the name suggests, it is bluish in color. So one of the things with the acid-base world is we try to be consistent. And what you're going to see is that a red color concerning pH means acid, and blue colors represent base. And then we have all of these colors in between. So if I go back and take a look at the pH scale, look at what they did here. They put all of the reddish colors on one side, and these are the acidic side of the house. And then they put the bluish colors over here on the right-hand side of the house. This is your rainbow flag of pH, folks. Red, orange, yellow, green, blue, indigo, violet. RGBIV. There you go. So acids are red, bases are blue. That is the way that we interpret in the pH world what these colors represent. Red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. So with litmus paper, red litmus paper, because it's red, means acidic paper. And blue, because it's blue, basically means basic paper. That is what that represents. So let's say that I have two solutions, and in each one of these solutions, I'm supposed to measure the pH based on how it turns my litmus paper. Well, let's say that one of these solutions is acidic. I know it's acidic. Let's just pretend. And the other solution is a basic solution. Again, I know it's there. So the way that I do this is that I'll take my stirring rod and I dip it down into the solution, and I take the stirring rod and I place it onto the sheet of paper. One drop, that's all that it takes. Because this is acidic paper, if I put my acidic solution on the acidic paper and I do a drop, nothing changes. That means that my solution is probably acidic. It stayed red. That means my solution's probably acidic. But if I take a drop of my basic solution and I put it onto the red paper, one drop, bloop, there it goes. If that solution changes my red paper and I get a blue dot, that blue means base. That is confirmation that the solution that I just put onto that pH paper is a basic solution. The same thing happens with the blue down below, but opposite. So if I take my acidic solution and I put it on blue paper, my acid is red. It should go red. So that drop of solution will make that blue paper turn red. There's the confirmation that I have an acidic solution in my beaker. Well, I do the same thing with my base. If I put the base onto my blue litmus, there goes my drop. But folks, my base is supposed to be blue, and that's blue paper. So I'm probably not going to see a color change. So here is an image of litmus paper, blue paper, red paper, and over on the right-hand side of your screen, what you're seeing over here is basically the red litmus paper at the top, where we have spotted or dabbed some solution on the end of it. And it turned that paper bluish. So that means a base was placed onto this sheet of paper. Down here at the bottom, this is my blue litmus, blue all the way, and then I put a dab of solution onto the end, and that paper turned color, and it turned red. So that means the solution that I have used is an acidic solution. The third one that we normally do not talk about or do not use is this thing called neutral. And neutral is kind of a one-size-fits-all. So in the neutral paper, this is not really red, it's not really blue paper, but it's more of what I would call maybe a greenish color quite often. And I know it doesn't look green in the picture, but a drop of solution onto this paper, if that drop turns red, it's acidic. If that drop turns blue, it's basic. So this is a very quick go-to, almost like a universal sheet of paper. But when I say universal, we actually have something a little bit better than that. And this is one of the reasons that we don't just mess with neutral litmus paper, because we have something called universal paper instead. So the nice thing about universal paper is it's not just red and blue based. You actually see all of the colors in the middle. And this paper will change color depending on the pH of the solution that you give it. So deep, deep red will be a 0.1 pH, and really dark, dark blue colors will be a solution of 12s and 13s. But the paper could also turn yellows and oranges and greens and blues and purples. So here's an image of just strips of paper that we have placed different solutions on, and that paper has turned color depending on the pH. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Maybe that's how you want to imagine that. But you see reddish on one side, more bluish purple on the other, and all of the colors in between. So what would happen is that if I had a solution in the lab, I wanted to know a quick pH of it, I would dab a drop of that solution onto a universal indicator paper, and then I would match the color up to this scale. Very easy to use. It doesn't really take a lot of training at all in order to use paper the right way, which makes it very nice in a lab environment. Well, it's not just paper-based. Folks, I can also have solution-based indicators as well. So what you see here is a test tube rack, and that rack has different solutions on the inside, and those solutions have changed color based on the pH. So I have maybe a liquid indicator, and I add a drop or two of that same liquid indicator into each one of these test tubes, and based on the colors that they turn, it will tell me what pH levels that solution or those solutions are going to be. Very similar to the paper, very similar to the scale that you see on the casing of the paper, but it's just reagent based. It's a liquid based reagent, right? Well, as you can imagine, this is not the best way to detect pH, especially if we need a concrete value. So we do have things called pH meters in the lab as well. The problem with these is that it requires a little bit of training. We have to tell you how to use them. You have to be comfortable with them. We have to do what we call calibrate them. We have to make sure they work the right way. But it is a piece of equipment that is used in a laboratory all the time. So this pH meter that you're seeing, the other drawback is the price tag. This is about $350. So this is one of the cheaper versions of a pH meter, believe it or not. So $350 is pretty good. It can only measure pH, and that's about it. On the screen, what you're seeing are the great big number 7.11. That, of course, is the pH value. pH value can change depending on temperature. So that's what you see down below. This is the temperature of the reading as it's happened. So sometimes we have to write down those values just to make sure that nothing funny is going to happen with room temperature in our readouts. All right. So there's one example of a pH meter. What we have in our laboratory, though, real pH meters, are these VWR Symphony meters. And the Symphony meter they thought was pretty clever because, look, they put pH into the middle of the name, right? These meters are a little bit more expensive. That's because they're better meters, and I'll talk about that in just a second. But these things run for about $800 a pop. And the probes that get attached to them do go out and they do go bad. So we have to replace those as well. So $800 for an initial investment, pretty rough. And then these little probes that we stick down into the solutions, those have to be replaced as well throughout the time. So it's just something that runs into money if we're not very careful and if we don't take care of them the way that we should. Here's another portable pH meter. This portable pH meter, $60, pretty cheap. It's meant to basically put in your pocket and go. So if you do environmental testing and the environmental testing requires you to do the testing or some of the testing at the location, then these are very portable. They're very small. They're not the best pH meters, and that's one of the reasons that they're so darn cheap. It gives you an idea, but by no means is it the best measure of pH that we can do in a lab environment. Something else that we have in our lab are portables, but these are more what I would call the basic side of the house of the portables, and these are the vernier pH sensors that you will probably be using in this lab. So here's a pH probe. This probe goes down into the solution. This is what measures your pH, and that probe is connected to basically the pH meter. And for this, it's actually the LabQuest device. The LabQuest is designed to be the pH meter part, and your probe gets connected into the meter, and this meter will give you a readout of the pH. This is not what the pH screen looks like. This is just a stock image of the LabQuest 2 device. When you plug in your pH probe, you will see just a green screen, and it will say pH equals, and then it will give you just a big fat number right there in the front of the screen. That's all that you have to write down. All right. So again, just some terminology. This piece is called the probe, and this piece is called the meter, right? The VWR image. This is the pH meter, and what's connected to the meter is going to be the probe. And then the HANA pH that you're seeing here, same deal, folks. This is your meter, and this is your probe. A lot of people get those confused, and that's why I'm stressing that. All right. Next up, I told you that some pH meters are better than others. Why? We look at three things. We look at what we call pH range. And in this image, it looks like the pH meter that I have captured here, which was our probably VWR, goes to -2 to 19. So if you have solutions that go below a -2 or above a 19, this pH meter is not going to work for you. Some of these pH meters, if they're cheaper, have a smaller window. Some of the more expensive ones have a larger window. pH resolution is something else that we look at. So pH resolution is how low can we go? It's like a game of limbo. So 0.1, 0.01, 0.001. It gives me some choices. So how do I want the pH to be displayed? And this pH meter will actually report the pH in 3 decimal units if I want it to. The issue here, though, is that most of the time, pH is recorded with 2 decimal places. Okay? And then finally, the pH accuracy. This is kind of stated a little weird, less than 0.002. That means if it reads like a 7, if it's supposed to read a 7.0000, that accuracy number means that when I put the pH probe into that solution and measure it, well, that pH probe is pretty good because it only can go 2 below and 2 above. So if it's a true pH of 7 solution, if my probe is working the right way and my meter is calibrated, then that is the very tight acceptable window that this probe and meter will give me. So pretty darn good, if you ask me. But most of the time, again, we report pH with 2 decimal places. That's pretty much it. That's pretty standard. Notice something that I did say, though, was calibrate. We have to make sure that our pH meters are calibrated, and that's the purpose of the buffers. So 4, 7, and 10 are the 3 standard buffers that we would see most of the time when we are working with a pH probe. And 4, 7, and 10 basically creates what we call a calibration curve to ensure that my meter is working the proper way. Now, that's a little bit too much for you to take in right now, but keep in mind, it's a piece of equipment. How can I ensure that this piece of equipment is giving me the proper number? I can't just take this out of the box and stick it into a solution and hit read. I have to make sure that it's primed. I have to make sure that it's calibrated. I have to make sure that it's ready to go. Very similar to you hitting the tare button on the balance. We want to make sure that this instrument is working the proper way, and that's the purpose of the calibration buffers. So we typically use 3, and we typically use the 4, 7, and 10 as the pretty standard buffers that we always use. All right. So what that means is that if I go and get a pH meter like this one, before I do any measurement at all with it, I will take out my buffers and I will go into a calibration section. Look, right here on the screen, very first button, you see that abbreviation CAL. That is going to stand for calibration. We do it all the time. So what that means is that I'll put my buffers onto this meter and probe, and I tell it, this is pH of 4, this is pH of 7, this is pH of 10, save it. And now it's going to use those measurements, and it's going to reference those measurements and those buffers when I start dipping it into the solutions that I want measured. All right, so with the lab procedure, folks, it's pretty standard. What you're going to do is that you'll have a data table. You're going to check these solutions. You won't know what they are. With blue litmus, write down what color that they turn. Then you'll check them with red litmus, write down the color that they turn. Then you'll check it with the pH meter, write down the value that you're given, and then define these as an acid or a base based on the observations that you have made with these solutions. Very straightforward, very quick lab. It's not going to take much effort on your part at all. And then you'll just go through and answer some of the questions that happen at the end of the experiment. So have fun with the pH. It is a general intro, getting you used to a pH meter, getting you used to the litmus paper all over again, and this definition of an acid or a base. All right, so with that said, I'm out of here, and I will see you, or somebody will see you in the lab ready to go with this very brief, short, probably 30-minute to an hour lab on your pH measurements. Good luck.